Hello everyone. In this session, I'm going to talk about how we can very well use random forests for binary response variable. In our previous session, we talked about using random forests for multiple category response variable, whereas now we are talking about the same classification problems, but instead of multiple categories, which is greater than two categories, here we are talking about exactly two categories. And how do I really group the data into one of these two categories? And how can I use different techniques of random forests to do the classification of the data into two groups? So here I'm going to talk about two major algorithms, right, using different implementations in R. So one is binary response random forest, the other one is binary response random ferns. So these are the two algorithms that I'm going to design and explain you in this context in this session. For this, we are going to consider our data that is related to diabetes, which we have used for a few other binary response variable related models. So this contains, for a quickness, let me just try to bring in the data again. So this is the diabetes data. The dimensions of the data wise, I see that it has 600 rows and 7 columns. And a quick summary of the data tells us that it has these particular attributes. The diabetes is the variable that is having a negative and a positive. Age is something that we are expecting that it will influence the diabetes. Pedigree, the mass of the person, the pressure, the glucose levels, and the month of pregnancy. So these are the various elements that we are considering which could influence whether the person is having diabetes or not, and using our random forest we want to check that out. And because this is having a variable with only two outcomes, the response variable has only two outcomes, negative and positive, I am treating it as a binary response variable. And now any random forest that I am applying on this data comes under the binary response variable based random forest. And now because this data contains a few NA's missing values, it's better that I clean up the data by doing na.omit. I'll do an na.omit on the same diabetes and reassign it to the same variable diabetes. Now I could see, if I am looking at the dimension of diabetes, now it is containing 564 rows and 7 columns. This would be the data that we will use for the modeling purpose out here. Both the models, both the algorithms, we are going to execute with that specific data. So here, when you are talking about the binary response random forest, we are executing it using the package random forest with the random forest function itself, which means it is exactly the same as the classification random forest that we have used earlier for multi-category classifications. Because there also we have used the package random forest, and the function again is a random forest function. So I really don't need to go into the detailed explanation of the same, because the whole thing that we have used is exactly the same. We are setting the number of trees to grow in that random forest. We have to set the importance to be true so that we will get all those variables which are influencing the dependent variable, and proximity is equal to true will really give us the how close each of the observations are in the data. So this is what we can directly give, and probably as an assessment of the model towards the end, just like the way we have plotted the kappa statistics, we can also use the ROC curve right? So receiver operating characteristic curves, we can very well plot it to really see what is the classification of the true positives versus the true negatives as a part of our predicted model. We have seen earlier, I had taken a session separately where all these different kinds of performance measures have been discussed. So for all the further details, you can very well refer to that video wherein the ROC package, ROCR package and ROC curve as such are explained in detail. Here I am just going to implement the ROC curve. Based on the curve, let's make some kind of inferences regarding the prediction and the accuracy of the prediction being plotted. So we will load this ROCR package as well along with the random forest. Random forest is actually doing the whole classification part, the whole modeling part. After the prediction is being done, to really assess the goodness of the model, we are relying on the ROCR package. So basically, this is more for performance assessment. This package does not play any role in terms of building or predicting the random forest. Once the whole predictions are over, we are using the ROCR package to primarily track the accuracy of the model, get to a final assessment of the accuracy of the model. So let's load the package. So I am loading library random forest. Loaded. We are also loading ROCR. I want to load this package ROCR also, so that towards the end I will be using it. Now I have got the data. The binary response variable is there. Yes and no are the two things that are there, are negative and positive are the two things that are associated with this binary response variable. Now I can split the, so preliminary checks are being done already. Wherever there was NA in the data, we have removed the NA values using NA.omit command of R and reassigned it to the same variable. Now I need to split the entire sample into a training set and a testing set. If I am going on that 564, if I am going for 70%, it is around 395. So I will take 395 as a part of my training data. So let me set the seed at 1000. Let me take a variable called train, which will randomly sample out 395 values between 1 to 564. It will sample 395 values randomly without any kind of replacement. Means 395 unique values between 1 and 564. And based on that, I will get my training data. The training data that I am going to get is a subset of diabetes. The training data that I am going to get is a subset of diabetes, wherein I will consider the rows that are there as a part of the train and I will consider all the columns. Whereas the test data also is another subset of diabetes, wherein I will consider the rows that are not there as a part of the train, but I will consider all the columns. So that's how I get my training data and the testing data created. So the training set and the testing set are typically separated. Now I can get into the process of building the model. Random forest is the name of the function that I can very well use. I can set the number of trees and at the same time I can set the importance as well. So I'll take the fit variable which will contain my random forest. So I'm giving the random forest as an input. So my dependent variable here is diabetes tilde. Independent variables, I'll take all of them. So I'm taking a dot. And the data that I am using in this case is the train data. That's the entire data that I'm using. Right, the whole data is what I'm considering out here. Then I can very well set the entry, which is the number of trees. Let me set it to some 1000. I'll set the importance equal to true, and even the proximity I'll set it to true. M try I will leave it to the default. Right, the number of variables that need to be taken as a part of the tree fitment. So by default it will take the square root of the number of variables. I could see that there are 6 variables in the process, so square root of 6 is 2 point something. So there is a chance that 2 variables will be taken as a pair in terms of building of this particular tree. So let's see that, right, a number of variables selected at each split. I'm expecting that the default would be true, would be 2, but I can very well play around to 3 or 4, and I can go ahead in terms of creating different sets of models. So the random, I mean the first by default kinds of settings for all other things have created this kind of a model. Let me quickly check what has come out of this model. Right, the random forest, this is the formula that we have given. There are 1000 trees to be fitted, number of variables tried at each split. So the M try by default is set to 2 here because it will take the downward side of square root of number of variables. We had 6 variables in the data, so square root of 6 is resulting in 2 point something, and the lower side integer of the same is 2. That's the reason 2 variables are taken at each of the split. And here it comes out that out of the bag error estimate, when we are looking at the training data per se, the out of the bag error estimate came out to 35.3%. Remember, this is on the training data, not on the testing data. And this is how the classification matrix or the confusion matrix typically came out. So negative, with respect to predicting the negatives, the model was decent enough where you have got only a 13% error. But when it came to predicting the positives, probably the error is almost to the extent of 51%. Right, you could see only 62 of them are correctly classified, whereas 65 of them got wrongly classified. So the model could not do a good job, especially in terms of predicting the positives, those who are positive to diabetes. But for those who are negative to diabetes, at least the model was able to do a decent job. And overall estimate of the error rate is around 25.32%. Now on the top of this, so now if you could see, we have used, even if I do the print, just a fit or even a print of fit, both should give me the same outcome. And so it has given me some kind of a details like the out of the bag error, and it also has given the class specific error. So which classes are predicted more accurately and which classes are not predicted accurately is being given by the print command. Now I can very well visualize the error rate by iteration. So for each iteration, after how many iterations the error rate has actually stabled out, the overall out of the bag error as well as the class specific errors. Right, we have said we will build 1000 trees. So when did they get stabled up? Is it that they got stabled up at least even after 1000 iterations, or still much before itself they have got stabled up, or even after 1000 iterations do I see that the error rate is still fluctuating? So I'm more interested in looking at the misclassification errors, both the out of the bag errors as well as the class specific errors. Are they settling down to a stable range after a certain number of trees? So that is what I can do by looking at the plotting of the fit, which is my model. Now you could see that this is what the black one is your out of the bag error, you could see that it has almost stabled off after this stage, after 200, 300, or probably even from this stage, I could see that it has stabled off. The same logic goes even with the downside, right? Even with the negative group also, the error became more or less stabled off. With respect to positive, I see a lot of jumps that have come out here, but after 600 or something, I see a lot of stabling off even with the positives. So this is what I could see with respect to the errors associated with both the classes. This is the positive class where it is lying around that 50 range. This is about the negative class where it is lying in that 10s and 12s kind of a range. And probably this is what is the out of the bag error, which is between the 20s and 30s. And I could see where the overall error got stabled out after what number of trees. So this is one thing that we are assessing when we have fitted a model. And along with that, I'm also interested in looking at the importance of the different variables. So I can go with the importance of fit. So now you could see it has gone with two different. One, it has taken the mean decrease in accuracy kind of a model. So wherein I could see the glucose has resulted in very much higher mean decrease in accuracy, a very much higher mean decrease in accuracy. Whereas the next comes the mass. This has resulted in a decrease in the mean decrease in the accuracy. So probably if I have to classify that particular variables which are very significant, I could clearly see that glucose is one major variable, because if I remove that, the accuracy is going to fall down drastically. And at the same time, I'm also looking at the mass. Even if this is removed, the accuracy is going to decrease quite drastically. But there is no such sign with respect to the pressure. If I remove it, probably it says that the accuracy is going to increase rather than decrease. So probably that is where I could see that pressure could be a completely unnecessary kind of a variable. Whereas when I'm looking at the glucose or mass, they are more and more significant variables. Even with respect to the Gini coefficient decrease, we are seeing the same. The first place goes to glucose, the second is going to mass, then comes the pedigree and so on. And even in this case, I could see that the pressure is having the least possible importance in the overall process. Even the graphical plotting of the same comes with var imp plot. So I am talking about the variable importance plot. For the fit, I can look at, I could see that the glucose is looking like very heavily influencing one. Then comes the mass, then the age, pregnant, number of months of pregnancy, and pedigree, whereas the pressure is coming towards the last in this case, and even here the importance is coming out more or less in a similar manner. So I can either use the mean decrease in the accuracy model, or I could very well look at the mean decrease in the Gini coefficient to assess which variables are extremely important and which variables are nowhere contributing to the model. So that's one more thing. So up to here, let me look at the overall context. So we have calculated the variable importance scores. So they are calculated, one using the mean decrease in accuracy and mean decrease in Gini score. Based on that, we are able to assess which variables are highly important and which variables can very well be ignored as a part of understanding of this model. And once we are done with this, it's better that we look at the tenfold cross validation. Especially if I have more number of predictors, it will really help me in identifying what is that optimal number of predictors for me to have. So in that, because it will play around with the different combinations of the predictors, it will keep reducing the predictors to finally narrow down on the goodness of the model. So I can very well try out the RFCV, which is which is where we are doing the random forest cross validations, which we can do it as a tenfold cross validation or something. So I can quickly look at for the structure. I will look at the RFCV. So okay, so I have to give the train X and train Y separately. So I am calling CV as a variable, wherein I have to provide train X, which is the matrix or a data frame containing the predictor variables, right? So I have to give only the predictor variables. So I can very well take diabetes. So I have to give this function as RFCV. Within that RFCV function, I am train X. Within the diabetes, I am taking all the rows except the seventh and all the columns except the seventh column. That would be my train X. My train Y will be a subset of diabetes. Sorry, not diabetes. I have to take it as train data. I am taking a subset of train data wherein I am selecting all the rows, all the columns except the seventh column. My train Y is again a subset of train data where it has taken all the rows but only the seventh column. So these are the two inputs that I am giving. The CV.fold, I'll generally go with a tenfold cross validation instead of the default 5. So I can set that as a tenfold cross validation, and I can very well set all the things that are associated with my random forest. So mtry I can still keep it as 2 itself, but if required I can very well play around with the mtry. But recursive, where the importance of the variables need to be recomputed at every step, I will set that recursive as true. Then entry, which we have used in our model, I want to set it at same 1000. And importance I am setting as true. Proximity also I want to set it as true. So that's how I want to do my tenfold cross validation. Something went wrong. Error in random forest default. Let me look at the dim of train data. It is 395 rows and 7 columns. Train X matrix or data frame containing the columns of predictor variables. Let me just try X, which is train data, all rows except the seventh column, and Y, let me just set it as train data all the rows and the seventh column only. So once I take these two, let me just check CV now, wherein I am considering RFCV, where I am giving only X comma Y. So X is the train X, Y is train Y. Formal argument importance matched by multiple actual arguments. Okay, importance. Let me remove the importance part from here. Let me just keep only up to here. Yeah, it looks like the importance is having a problem out here. So once I remove the importance, there is a cross validation that is performed, right? Now with the cross validation, now if you look at the cross validation that got performed, it has tried different levels 6, 3, 1. These are the different number of variables that have been tried, and these are the errors at each of the cases. So I can very well plot CV dollar n dot var, CV dollar error dot CV. I can do a plotting CV dollar n dot var, CV dollar error dot CV. When I'm doing this plot, it's better that I go with a line plot so that we can see how things are moving. Type equal to L. So this is telling me that this is how the whole thing has fallen. So after 3, anything beyond 3, you could see that the reduction in the error is quite lesser, but from 1 to 3 variables, I could see that the reduction in the error is quite higher. So this is what you could say, that there are at least 3 variables which are significantly contributing to the model, but after that the contribution of the variables is much lesser. So the top 3 variables could be contributing very much to the occurrence of the diabetes versus the non-occurrence of the diabetes. So this is what I could see with the n-fold cross validation. We have done a 10-fold cross validation using the function RFCV. After that we have done the plotting of that same, right, the plotting of this errors versus the number of variables, and based on that we have looked at how the cross validation error has actually gone down as the number of variables, as the number of predictors is increased, but beyond a certain stage increasing the number of predictors also did not make much of a change in terms of reducing the overall error. And if you really want to try, you can very well try different options of mtry, right? You can try, by default here the mtry is being 2, but you can very well make it to 3, 4 and try out different kinds of options that are coming out. You can very well manage the control the number of variables randomly at each of the split. So wherever you want to change, instead of 2 you want to change it to 3 or something, you can very well change it. You have actually a function called tuneRF. This tuneRF can actually give you how, see, basically I want to use this is a very interesting function which will give you what is the best mtry for your data, right? We can use what is called as a tuneRF. Let me just run through that function, very interesting function here, which is doing the reverse workout, starting with the default value of mtry. So the default value here is 2. It searches for the optimal value, so it tries to minimize the out of the bag error estimate, and based on that it will give you what is the best value for mtry. 1 you can try, 2, 3, 4, 5, whereas this, if you are using this tuneRF, you could very well give what would be the best possible value of mtry for this data. So you can give x, which is a data frame of predictor variables, y, which is a response vector. So factor for classification, numeric for regression. So because this is a classification related, it should be a factor related variable. mtry start, I can very well say the start is with the default. So I can very well set mtry start equal to true, 2. Then we are trying how many trees to try, number of trees used at the tuning step. So I can, by default it is 50, but I can very well set it to the same 1000 which we have used for building of the tree. So I want the entry tries to be 1000. Step factor. So at each iteration, mtry is inflated or deflated by this value. By default it is 2, but I can very well set it to 1 because I have very few number of independent variables, so I can very well go ahead by inflating it by a factor of 1. Then the improve, which is the relative improvement in the OOB error, that must be at least by this much amount for the search to continue. If the improvement is at least by 0.05, or I can set it as 0.01. If the improvement is at least by this much amount, then only the move goes to the next value of mtry. And trace is true is talking about the progress of the work will be showcased on the screen. I can also go with the plot where the OOB error for each different value of mtry will be plotted, so that I can easily identify the best possible value of mtry. And finally, it is also asking me whether to run a forest using the optimal mtry value that is coming up. If I want to set it as true, even it will do the running of the random forest based on the optimal mtry value that is typically found. So we can set all these things, and based on that we can do the tuning of the data. So I can very well set the best mtry, wherein I am using tuneRF as the name of the function, best mtry. I am using tuneRF as the name of the function. X is my X itself, Y is my Y, because we have already set them from the training data. mtry start, I can set the starting value of mtry as 2. If I don't set it, it will take the default. Default is the same as in the case of random forest, so if I don't set it, it will take the 2 itself. Entry tree, which talks about what should be the trees, number of trees that need to be fitted. I'm setting it equal to 1000. Step factor, the default is 2, I will set it to 1. The improve, the default is 0.05, I'll set it to 0.01. The trace, I'll set it to true. Plot, I'll set it to true. Do best also, I will set it equal to true, so that I want it to really go ahead with the model also. So there is a fine tuning that is happening in the process. Okay, so it has found only one. There is only one mtry that it could have got. It has got only mtry equal to 2 is what it has finally gotten, because we have set the step factor as 1. So it has tried 1 as well as 3, but finally it could get only 1 as a part of the mtry, and finally the out of the bag error ended up at 25.06. But let's say if I am redoing this model, where I am starting with an mtry of 1 instead of 2. This is where I can get both. So in this case, mtry has come out to 0.06. Okay, step factor, let me set it to okay, if I am setting the step factor to 2, this is where I am getting different possible values of mtries and their corresponding errors. I am seeing that the minimum error is coming when there are 4 when there are four different variables that are taken as a part of four variables are taken for building the model rather than only two variables that for building the forest. If four variables are taken compared to either two variables or six variables, it looks like the out of the bag error is much lesser. Now what I can very well do is I can use that 4 as a kind of a base for redoing my model. Right, I can use this 4, I can create a new model where I can very well set, right, not the RFCV model. I can go ahead with the random forest model. I'm going ahead with the random forest model where I'm setting m try equal to 4, and based on that I'm redoing the model. So now the fit is coming out like this is how it is coming. The out of the bag error came down to 24.05%, whereas earlier it was around 26 something. And even the negative, the classification is coming out like this. Only 13% of the negatives are wrongly classified, 45% of the positives are wrongly classified, and this looks like a better model. So once I know this, I can very well go ahead in terms of predicting this model on the testing data. Right, I can go ahead with predicting this model on the testing data. So I will use the predict function where I am using the fit, that is the model, and the data that I am using is the test data without the seventh column. All the rows I am including, all the columns I am including, but without the seventh column. So based on that, I could clearly see the predicted values are, so this is how the predicted values, some of them positive, some of them negative. So these are the predicted values that have typically come out. And I can also look at their probabilities as well, right? Instead of just looking at the numbers as it is, I can also type, I can set the type equal to prob to get the probabilities of the values. So now you could see the predict comes along with the probabilities of both. What is the probability that it belongs to, that a value belongs to negative, and what is the probability that it belongs to positive. So I can very well take only the probabilities that it is belonging to one group, which is the diabetes being positive. Now I will use my ROC. To build the ROC, I want that particular value for which I'm more interested in, which is the positive is the value I am more interested in, a person catching diabetes, right? So this is where one I could have done a simple error estimate there. Okay, let me do both the things. The first thing, let me remove the probability. I am only going with the classes. So based on that, I'm getting the classes as something like this. I can create a table where I am having the predicted value as well as the actual value is coming from the test data, the seventh column of the test data. Based on that, the table it is saying 92 negatives are correctly predicted, 31 positives are correctly predicted. So 123 values are correctly predicted out of the 169, resulting in an accuracy level of around 72.78%. So this is what we are able to see with respect to the goodness of fitment of the model. But if I have to go with the ROC, the receiver operating characteristics for the training data set, right, I can very well, or for the testing set, I can very well say the predicted instead of taking the value, I should take, instead of taking the class to which it belongs to, I'll take the probability, because that is the base for me to work out this one. So when you are looking at the spread here, you are getting the probability that it belongs to negative as well as positive. Now I will take spreads, which is only the probability associated with the variable of my interest. So this is where I will take the spread and the second column only, which will give me that only relating to the positive. What is the probability that a data belongs to the positive group is what is coming out here. And from the ROC, I can very well go ahead with the plot function, wherein I am looking at the performance. If you remember, the performance function from the ROCR, it does all kinds of predictor evaluations using this function. So all I need to give is, as an input, first I need to do the prediction function. Right, let me let me do the prediction function also here. So the prediction function is every classifier and evaluation using ROCR starts with creating a prediction object. So I have to create a prediction object, one based on the probability that the value belongs to the particular group. So I will take the probability that it belongs to the positive group. Right, I have to take this prediction, the vector matrix containing the predictions. So I am giving the first thing is the probability that it belongs to the first class, and I am also taking the actual data. I am also taking the test data, which is the actuals, and based on that I have to specify the true positives versus the false positive responses. So this is what I really need to consider. So in the predictions, I am simply taking two inputs. One is the predictions, which is a vector or the matrix, and the second one is the label, which is typically containing vector matrix list or data frame containing the true class labels. So they should have the same dimensions as the prediction. So these two are the ones that I am going to consider. So the first step for me is, I can very well consider the prediction of spreads, which is the probability that it belongs to a particular that it belongs to a true class, and the second one that I am considering is the testing data. I am looking at the testing data with the seventh column alone. So based on that, I am able to create a prediction object. So I could see that in the prediction object, these are the things. So the number of positives, now you could see right from the beginning, it has actually computed so many things once I have created the prediction object. So these are the values, these are the probabilities, these are the labels. So the cutoffs are being decided, and based on that, these are the false positives, these are the true positives, these are the true negatives and false negative. So you could see that number of positives are 65, number of negatives are 104, and number of positives that are predicted, these are all the positives that are predicted, number of negatives that are predicted, so these are the negatives that are typically predicted. I can very well go ahead by looking at the performance of all these predictions that have typically come out. So I can very well go ahead in terms of understanding the performance of all these predictions that have come out. Performance of this prediction, let me look at the performance one. Yeah, performance, I need to give the predictions as the input, and I also need to give the measures. So basically for the measures, there are various other things that I should give, either FPR, TPR, these are some of the measures that I have to give for an indication. So what I can very well do is the performance of this, and I can very well say TPR which is the true positive, FPR, which is the false positive. I'm more interested in looking at this part. So I could very well get the performance analysis of this. We are getting on the x-axis, we are taking the false positives. On the y-axis, we are talking about y-axis, we are talking about the true positives. And these are the x values that are being considered. These are the y values that are being considered. Now I can very well go ahead in terms of plotting this performance altogether, which will give me my ROCR curve. I'm taking a plot of all this. So this is how the plot is coming out. The more and more closer this plot is towards the 1, the more is the accuracy of the model. The more it is closer to this 45-degree line, then it is not that kind of an accurate. Your ROCR curve is directly giving you a kind of an association with respect to the accuracy of the model. If you want, you can very well plot a straight line using your AB line function, where you can set A equal to 0, starting from A equal to 0 to B equal to 1. Right, you are going from A equal to 0 to B equal to 1, you are drawing a line. So you can very well set a line from A equal to 0 to B equal to 1. So this is the kind of a line. And the more and more closer this particular ROC curve to this particular line, we can say that the classification is nowhere doing a good job. The more this is away from this line and more closer towards the borders out here, this is where we talk about the accuracy of the model to be much higher as well. So these kind of calculations we can quickly look at to really assess the goodness of the model. Anyhow, we have tested this on our test data as well, resulting in an accuracy of somewhere around 72 to 73 kind of a percent. So that's how we can use the random forest model to do the prediction, and not necessary that random forest will always be the best model. Even in this case, I don't think it has arrived as the best model for the binary classification data. But that's how we can really plan around using a technique. The more and the more the number of techniques we know, we can experiment with all the techniques, and finally whichever is the one that is resulting in a much better prediction would be the choice for us for predicting on a new set of data as well. Right? Now, looking at binary response random ferns, right? For the same objective, instead of using the random forest, we are talking about the usage of random ferns. Even this one, we are executing it through package rferns and the function rferns. We have already used that even in case of multi-category random ferns as well. Even there we have used the same package and the same function, so I don't need to really stress upon that again. So just for a quick refreshment, I can just for a quick reminder, I can very well load the function to have a quick reminder. But I don't want to go in depth because we have already discussed all the attributes that are associated with the rferns. Here also, just to differentiate, I would use the ROCR package, and based on that I would also plot the false positive rate versus the true positive rate as a part of the chart to see what is the area underneath the curve, AUC curve, what is the area underneath the curve to really assess the accuracy of the model. So that part we are still going to look at here just for a quick practice. But the rferns per se, we can directly use it. I'm not going to discuss more and more about it again. So I'm loading the rferns package. Right, so it is loaded, and quickly looking at rferns as a function, we know that we have to give few important things out here. We are giving a formula, we are giving the data, we have to specify how many ferns we are fitting. So probably I can still think of fitting some 5000 ferns, I want to go with whether I want the importance. I can set the importance to true so that the importance of each of the variables can be computed. Instead of none, I will set it to true. Report every. So because I am going with 5,000 ferns, I can think of reporting for every 10 ferns or every 25 ferns. So I want the OOB to be reported for every 10 ferns or 25 ferns. I'll say save error propagation as true so that the error would be displayed to me at the end of each of the 25 ferns or 10 ferns. So those are some of the inputs that I'm going to give to this model. So what I can do is, once I have loaded this data, everything is there with me, I will go ahead directly with the fitment process. In the fit, I'm going with R ferns, where the diabetes is my binary response variable. Tilde, all other variables I'm taking them as explanatory variables. The data I'm taking as a part of my train data. I'm considering my data as a part of the train data. Ferns by default, let me say the default is 1000, but let me set it to 5000 so that I can redo the process where the error is the minimum. I can have a plot of the out of the bag error for different number of ferns. I can see where the out of the bag error has come out to be the minimum most possible, and based on that I can really assess what should be the optimal number of ferns. So I will go ahead with that process. Then I can very well set save error propagation as true as a part of my model, and when I am saving that as true, I want report error every, let's say 10 ferns. For every 10 ferns I want my error to be reported, and importance also, let me set it to true so that I can get the importance of the various variables which are contributing to this model. So this is what is my new model, right? This is what is my model, which is the R ferns model. So running it, yes, it has given the OOB at the end of every 10 10 10 10 kind of a stage. We have pre-fitted 5000 trees, so that's where you could see here at the end of 10 ferns the error rate is 31, came down to 28, 27, 26, again went to 27, 26, 26, 27, 26, 26, 27, 26, 27, 7, 26, 26, 27, 27. So after a certain, so there are some 26s and there are some 27s that have come out in the overall process. After a certain point, I see that the OOB error is maintained at 27.595%, and somewhere towards the end it came down to 27.089%. But there are some 26s, that is where the minimum error has actually come out. Now if I want to see what is there as a part of the fit, I could see that overall error rate is 27.09%. The default depth of the ferns is 5, and there are 5000 ferns that we have fitted. This is how the classification matrix has come out, right? I could see that these 288 are correctly classified, whereas this 107 are wrongly classified, resulting in a 27.09 out of the bag error, right? So this I can do either with a fit or I can do with a print of fit. But what is more important for me is looking at this OOB error. So this is where I talk about plotting of fit dollar OOB error. So when I do a plotting of this fit OOB error, where I set the type equal to line, what it simply does is it tries to plot for different number of ferns, right from fern 1 to fern 5000. For a different number of ferns, it will try computing what is the OOB error, and it gives me all the possibilities. So this is how the OOB error has been changing as the number of funds got increased. Probably somewhere here I am seeing that the error is much minimal. In a few hundreds I could see that the error is much minimal, and this is what I can very well test out from the data by using the which.min. So which one has resulted in a minimum error of the fitment. So once I find out where the minimum error is coming out, it says 102. So when I have 102 ferns altogether, that is where I'm getting the minimum most error. And probably I want to find out what is that error. I'm again putting fit dollar $OOB error. I'm taking the subset of 102. I'm taking the subset 102, which says 25.82% is the minimum most error. 25.82% is the minimum most error. Now this means I need to go with those many ferns. If I go with just 102 ferns, that would be more and more appropriate for my data. Now this is where I can very well redo the process of fitment. So I can recall the fitted model. Now instead of 5000 ferns, I can very well say I want to go directly with 102 ferns. That's it. And I want to save this random forest so that I can use it for a later purpose. Right now I don't need any kind of a reporting. Right, the reporting is very important only when I am more and more interested in seeing where the error is actually cropping up. So I can very well save this forest. So the default anyhow is true, so the random forest can very well be saved. So this is the model. Now here I could see that up to 100 the error rate is 28.35, but now for this the error rate has typically come down to 25.8. So that's how the number of the error rate has actually come down, and based on this I can do a fit to understand, which tells me that the OOB error rate is 27.59%, and this is how the classification is typically coming out. So I can very well specify that these are the this is the kind of OOB error rate, and this is the confusion matrix that has come out during the process, and these are the number of errors that are overall coming out. Now let me look at the content part of it. We have got the necessary data. We have done the preliminary checks because it's the same data that we are working with. All these steps are by default taken care of. We have estimated the model using R ferns. We have set the error propagation to true so that we get the OOB computed at every stage, the misclassification rate computed at every stage for different number of ferns. After that, we have printed the model to understand the OOB, the overall error at each of the stages, the confusion matrix. So we have looked at all those things in detail. Now, once we have got the error rate for each number of ferns, we have checked out what is the typical error rate. And finally, we have seen for what number of ferns the error rate is the minimum. For that, we have used which.min to identify the location where the error is minimum, and I have taken the subset from the error associated with that particular number of ferns. So it was like 102 ferns where the error is the minimum, and when I have looked at it, it has given that 25.8% is the out of the bag error associated with that. Then I have re-estimated the model by setting the number of ferns to 102. So I have got the complete details of the model again. Now once I am done with that, I have to go ahead with understanding the importance of the model. So I can very well go with fit dollar importance. Right, from the fitted model, by typing in dollar importance, I get the importance associated with each of the variables. So I'm going with fit dollar importance. Now I could see that the importance wise the highest is associated with glucose 0.08. The mass is having the next. Now this is where I can think of ordering the importance, right? So I can very well take fit dollar importance of the first column. When I say the fit dollar importance of the first column, I'm going to get only this much. So I will go with the reverse order of this one. I will go with the reverse order of this one, where I'm going to get 2, 4, 6. So 2 is the first, 4 is the second, 6 is the third, and so on. Now I'll take the fit dollar importance and I'll take a subset of this order. So my rows should be something like this, and I'll take all the columns. So this gives me that glucose is the most important variable in determining the diabetes. So the highest importance with a mean score loss of 0.087, which it could get in 68 tries. Then comes the mass, then comes the age, and the pressure is the least out of all the variables. So we are able to make out which variables are important as well as which variables are least important. And we are getting a measure of by how much extent there is a mean score loss that is happening, right? I can very well look at to what extent there is a loss in the mean score associated with each one of them. And I can also see the number of tries that have actually occurred for arriving at these particular values, right? So that's how I'm getting the importance. Now once I have created some kind of a model, then my next job is going ahead in terms of using the predict function to predict the classes using the test sample. So this is where I'll use the predict as a variable, wherein I want to use the predict function using the model, which is a fit, and I'm using the test data. Obviously the test data should not contain the 7th column. So without the 7th column, I'm going ahead with the test data, and if I look at the output that I've got, it has simply given me negative, positive, positive, negative. So I will create a table of this where I'm taking the predicted values. The actual values are coming from test data from the 7th column of the test data, which contains the diabetes part, the positive or negative to diabetes. So the table shows that across the diagonal 76 and 51, 127 are correctly predicted out of 169, resulting in an accuracy of around 75.14. Approximately 25% is resulting in an error. So that is if I am looking at using directly the test data, and based on that if I want to create the accuracy of the model, that is one way I can use. But if I have to go with ROCR, where I am looking at ROC curve, looking at the area underneath the curve and all, I can very well do the predicting in this way, where I can very well go ahead with the type equal to prob. Now when I see the pred, I could see, okay, the type equal to pred also here has given me only the type equal to prob has actually given me the classification of positive or the negative itself. I could have done one more thing here, setting the scores equal to true. one more way, instead of setting type equal to prop, in this I have another option where I can set scores equal to true. When I do this, this is where you could see the pred is giving me the scores. Both the positive as well as negative values are there where I am getting the scores. So I can very well look at the scores. So these are the raw scores for me from the test sample, and I want to convert these scores into a 0 to 1 kind of a range. Because these scores have some kind of negatives as well as positives, I want to convert all these scores into positive. Now this is where what I want to do is, I want to this scores, I want to add up the minimum most value, or I want to subtract the minimum most value from each one of them. Or it's as good as saying I want to add up the absolute value of the minimum most value. So I'll say absolute value of the minimum most value of pred. Just add it to all this. Or it's as good as subtract the minimum most value from all this. Now based on this, I've got my new values of pred. Now wherein all these values are positives. There is no negative value, so I've just converted it all the negatives into positives. Now, because we want to use the ROC, first thing is I want to convert it into a prediction object. So I have to really take the positive, the one that is of interest to me. So I will simply create a prediction object using the prediction function, wherein the first thing I will take is, out of this spread, I am taking only the second column, which is that column that is of more interest to me, the positive column. So these are the scores that are associated with the positive column, and based on that I am also looking at the actual value which is coming from the test data from the 7th column. So based on that, the prediction object is being created. I could quickly check my prediction object. Right, the prediction object is giving me all these details. As we have seen, these are the predicted scores, these are the labels, positive, negatives. Based on that, the cutoffs have been designed. These are the false positives, these are the true positives, these are the true negatives, these are the false negatives. So there are number of positives are 65, number of negatives are 104. These are the number of positives that are predicted, these are the number of negatives that are predicted. Based on this, I want to convert this into a performance object. So this is where I can use the performance function on the top of this, where the prediction function would be the input. Along with, I have to specify what do I want on the x-axis and y-axis. So I'll specify the TPR, which is the true positive rate, and FPR, which is the false positive rate. So on the x-axis I am going to have the FPR, and on the y-axis I am going to have the TPR. So looking at perf, so these are the values that are associated. The false positive rate is the x-axis value, true positives is the y-axis value, the alpha name is the cutoff here, wherein these are the x values for different values of x, which is talking about the false positives. Then the true positives are also computed in terms of y, and these are the values that are simply plotted in the overall. So I could very well go with plotting of this performance, which is telling me this is the kind of ROC curve that has actually come out, and I can very well plot the AB line starting from A equal to 0 to B equal to 1. There is a single straight line that is getting plotted. So the more away this line is from the 45-degree line, the curve is more and more away from this 45-degree line, I can talk about the model being more and more accurate. The more it is superimposing, I could clearly see that the model is not much accurate. And we have a measure of finding the area underneath the curve also, right? The higher is the area underneath the curve, that's a measure of accuracy of the model. So I can very well check the area underneath the curve again using the performance function itself, where I am giving the pred, which is my prediction object, but I have to give within that, I have to type AUC, which will talk about the area underneath the curve. So based on that, I could see that the AUC, the area underneath the curve for me, is coming out to 0.808. So that's the level of accuracy of the model, the real accuracy of the model, talking about the area underneath the curve. So approximately zero point 0.8 is an assessment of a decent to good kind of a model. So that's how I can look at the area underneath the curve as a part of the ROCR graph, which can tell me what is the goodness of the model that I have fitted. So that's how I can use the random forests and random ferns for binary classification kind of exercises. So though there are many such kind of options that are available for classifying a binary variable, so we have already looked at decision trees, we looked at neural networks, we looked at support vector machines, now we are looking at random forest, random fern. As I have been talking of these things right from the beginning, there is no one algorithm which is a kind of a universally excellent algorithm for all kinds of data. The problem is the classification data itself, but we have n different solutions to approach that problem. The best way to look at all these algorithms is try with the same training data and all the algorithms, see, fit each of the models, and each of the models please run them on your test data to see which models are giving a higher amount of accuracy on the test data, not just from the accuracy or the percentage perspective. Probably you could also look at the kappa statistic, or just like now we have done, you can very well plot the ROC curve, and based on that ROC curve you could also look at the area underneath the curve to see a much better model of estimating the accuracy. So this is what I would like to cover as a part of this session regarding the classification, binary classification using random forest. If you have any further queries regarding the same, feel free to get in touch with me by giving me a call on the number that I have given below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.